In this lecture, we're going to talk about the null hypothesis, or maybe even better stated, the null hypothesis controversy. So there are some seminal articles on this. This is just a few of them, but Jacob Cohen wrote quite a bit about this in The American Psychologist. One of them is called "The Earth is Round," and then in parentheses it was p less than 0.05, and he was kind of mocking the fact that we use this p-value, and he was just really pretty adamant that this is not a way to do science and the null hypothesis testing. And we're going to go into the details of what he said in more detail as we go through the slides. Some other ones, there were APA said about looking at better ways to do null hypothesis testing. They suggested that effect sizes be used in all journal articles. They put out a call that from now on we want to see effect sizes, and we'll talk about what that is in the slides. And then 10 years later, they looked at it again to see how much it was actually being used. And it had changed a little bit, but there's still a way to go on this. And we still use null hypothesis testing. I still teach it. I'm very much at fault for teaching you null hypothesis testing. I want to make up for it by teaching you some of the inconsistencies of it. But it's used throughout psychology and other social sciences. And then some of the things we'll talk about at the end are just meta-analysis and ways we can improve on null hypothesis. So this is just some articles that you'll find in the learning management system on this topic. All right, so just as a reminder, we went over this a few weeks ago. We went over type 1 errors and type 2 errors. Anytime we do a study, we find a significant result, we could be correct that there really is a significant result out there, or we might have made a type 1 error. So a type 1 error is a false positive. We found something that really didn't exist. And so that p less than 0.05 is a way to state that might be the probability that the null hypothesis is true. And it's less than 5%, meaning that if we did 100 studies, on average, 5 of them would say we found an effect that wasn't really there. Like if we did 100 studies, I just made up some new medication, it's just a placebo pill, and I said it works on something, some great outcome. I try to sell it. I find 100 scientists who do a study on it. On average, 5 of them would find a significant result. And I could say that these 5 studies found this great miraculous result, even though I know it's a placebo pill. So on average, we're making type 1 errors about 5% of the time. And Jacob Cohen and others would say that's a big problem in our science, that maybe our journals, where there's been in recent times, in the past 5 to 10 years, discussion of replication. And some of the most major findings in our field haven't been replicated, and we can't replicate the results. Now maybe times have changed, maybe something, stereotype threat is one of those, and I don't want to pick on any. I think that's a very complicated and important literature to look through. Stereotype threat, one of the ideas was maybe it can't be replicated because it doesn't exist in the same form that it did when the original study happened. And maybe so, and maybe some of these others, it's just the generalizability to times at 30, 40 years later, maybe it's not the same. But it also could have been, and I'm not talking about any particular study, but there could have been a type 1 error. The study was published, we've taken it as fact, and over the years we've discussed this as if it's absolutely true. And the null hypothesis testing was not meant to necessarily, rule out all errors. We're taking a certain amount of risk whenever we publish a study. So that type 1 error could be a problem in our field. Type 2 error, on the other hand, is missing a result that, so we don't, in our study, we don't find a significant result. So we've missed finding that significant result. We've missed an opportunity to find something that really exists. So type 2 error can also be a problem. And we don't want to miss things, so when we can adjust certain things. We can adjust the sample size. So the larger our sample size gives us more chance of finding even a small finding. So I think of sample size as being a magnifying glass, that the bigger the sample size, the bigger our magnifying glass, the more precise we can find really, really small effect sizes. So sometimes we're looking at something that's a very small effect, and we need a large sample to find that. The other thing is, the bigger our effect size is, the easier it is to find that effect. So if we're looking at something that's a really large effect size, we don't need a very good magnifying glass. We can see it with our eye. So the bigger the difference, so if we're looking at an intervention, it's a really good intervention, it's easy to find that result. So the bigger our effect size, the easier it is to not make a type 2 error. And then the final part of not making type 2 errors is the alpha level. And so if we're less conservative, we're going to make fewer type 2 errors. So if we make our alpha level higher, we're going to maybe make more type 1 errors, but we're going to make fewer type 2 errors. So there's that fine line. We often use 0.05, but if we change it to 0.10, we're going to make fewer type 2 errors. If we move it to 0.01, we're going to make fewer type 1 errors. We're going to be more conservative, not take a null hypothesis unless we're absolutely almost sure that it's true. So that's how we can adjust and make changes for type 1 and type 2 errors. So again, with type 2 errors, we can look at sample size, and the bigger sample size magnifies the small effect so we can see it better, and then the bigger the effect, the easier it is to find. So another term that I didn't bring up before is power. And power is our ability to find an effect that exists. So it's sort of related to that magnifying glass example. So the larger our power, the easier it is to find an effect. So we want to power our studies, have our studies be well powered. Kind of a neat term to say I've got a well-powered study. But prior to doing this study, we can do a power analysis. So we estimate what the effect size is and how many people we're going to collect, and we can say how much power we have to find an effect. So that's something we could look at when we're designing our study, is a power analysis. And I'm not going into a lot of detail here. I can do that in a separate lecture, but just kind of bringing up this term. So Rosnow and Rosenthal, and I bring up these classic articles, and others have done this since, and it just makes sense, but this is a really good classic article, and they talk about these two researchers. So researcher Smith came up with this new intervention A, and researcher Smith found it was better than intervention B. And so let me make this a little larger. They found, here's the statistic, T degrees of freedom 78 equals 2.21, P less than 0.05. So researcher Smith thinks his intervention A is great. Researcher Jones, who came up with intervention B, says, no, my intervention's just as good, set out to prove Smith wrong. Researcher Jones conducted a study and found no effect. So no difference between the two groups. So researcher Jones says, no, there was no difference. So one thing to note here in these two studies is what's in parentheses, and this is degrees of freedom. And when we're looking at the differences between, so a t-test or differences between two groups, the degrees of freedom is related to sample size. So in one study we've got 79 people, the other study we've got 19 people, and so it's actually we've got 80 people and 20 people. These two studies vary just slightly in sample size. And maybe that's the reason they didn't find the effect. So when we break it down a little bit and we do some math behind it, we can actually find out that their effect that they found was actually this exact same number. They found the same result, but because they had different sample sizes, they had a different t-test. And that's part of the formula for the t-test, that the sample size changes our t-value. So our larger sample sizes, we get a bigger t-value, and a t-value that's bigger leads to a smaller p-value. So let me just simplify that. So the larger our sample size, the smaller our p-value, the more likely we're to reject the null hypothesis. And I see quite often in nutrition studies, the large Framingham nurses study, for example, they'll find that there was a study about electrical lines and people who live closer to, and I don't know if it's a Framingham nursing study, but it was another large study. People who lived closer to electrical lines had some bad outcome, maybe it was cancer or something like this, but it was such a large sample of people that they found a super small effect size. And the larger your sample, the more likely you're to find something significant. So in these big studies, they find tons of things that are significant. They may not be all that meaningful because it's a small effect. So eating canola oil versus butter, one might be better for you than the other, but it might be a really small difference and maybe not worth it to change your diet. That's probably a terrible example, but those type of things, they'll find a big headline will say they found a difference between these two things, but it's because they had such a large sample size. So this is one of the problems with null hypothesis testing, and I won't go into this in great detail, but again, this is the formula for a t-statistic. And on the bottom here we have the standard error of the mean. Standard error of the mean is the standard deviation over square root of n. So again, as this number n gets bigger, and we work this through, our t gets bigger. So if we have 1,000 people, our t is a lot bigger, which means our p-value gets a lot smaller. The probability of rejecting the null hypothesis becomes much bigger. So the bigger our sample size, the more likely we're to find an effect, just based on this formula. And that's problematic. And that's what Jacob Cohen said is very problematic. And in his article, in his work, he talked about why don't we use effect sizes? So rather than saying, is this significant or not? Is canola oil significantly different than butter or margarine? We should say how much difference there is. And it makes perfect sense in my mind. Why aren't we saying how much of a difference? Is cognitive behavioral treatment better than behavioral activation for depression? It's not really what's better, it's how much better is a better question. Would I be better served by getting this more expensive treatment? How much better served is a better question for me to answer if I'm going to spend money on this different treatment. How much do I gain from taking a multivitamin than not taking a multivitamin, or an expensive supplement? How much will I gain? What is the effect size? How much is a much more interesting question to me than whether it works, or yes or no. So Jacob Cohen advocated get rid of all of this null hypothesis testing. We don't care if it works yes or no, we care how much it works. And he said just use effect sizes. And his D, he came up with a value called D, is called Cohen's D in his name. And this Cohen's D is one example of an effect size. And if you hear the numbers, he talks about small effects, large effects, but there are many different measures of effect size. And I think it's vitally important for our field to advance to use effect sizes. We need to know how much this therapy works better than this other therapy, how much this medication works than this other medication. So rather than does it work, we need to say how much. Others have talked about maybe a way to improve it is to use a confidence interval so we can see kind of a range of values, and the larger the range, we know that the more the variability is in this range. So this is other solution to it, and it kind of makes some sense. How much of an effect we can find. Look at our range, like how much depression do we think will be reduced if we do this treatment? And we can look at the range of people who had this treatment and kind of say, well, 95% of the people had a reduction in depression from -3 to -6 points. throwing out random numbers, so we can see how much range we would have. So that tells us a little bit more, gets a little bit more at that how much question, and so I think it's a valuable thing to put confidence intervals as well in your research. Another idea I mentioned a little bit earlier in this lecture about replication and finding out the effect over time. We can do meta-analysis. And when a study has been done repeatedly, or when a treatment has been used repeatedly, each time it's been done, there's a different effect size. We don't necessarily expect the same effect size each time we see something published. And it might be different samples, and it just might be that it's an estimate. We have a sample, we don't have the population. So maybe this sample it worked a little bit better for this sample, or this other sample it didn't work as well. So we get different effect sizes. So why not aggregate all of these studies and average these effect sizes, and we get what is done in meta-analysis, an average effect size. So how much does cognitive behavioral treatment work for depression? We can look at the meta-analysis of this question and find out an average effect size. And that's something that I think is valuable, rather than just doing one study saying it's significant, yes or no, and then moving on. We can do meta-analysis to see if that result keeps coming over and over again. So one of the problems that we see in our science is what's called the file drawer problem. And this is, in this example, maybe we don't have file drawers anymore. This is going back to when paper was maybe a better analogy, but we would put things like studies, we didn't find a significant result, we put it in the file drawer. You know, like, gosh, we did all this work, but nobody's going to publish this study. And there are multiple reasons why people might not move forward with it. One, the scientist might say, well, it's not significant. I don't know if it's going to get published. I don't want to put the work into writing up the results and doing the study. So I'm going to just hold off on writing these results and put it in the file drawer. Maybe I'll do it someday. Journals may not want to publish it. The journal Science or the journal Nature, they're probably not going to publish something you say, well, I did the study, I didn't find anything, because they want to publish things that are significant. Journals want to become more popular, to be cited more often, and they're not going to be cited very often with a non-significant result. So only when you find something interesting. So maybe something that's controversial and not finding significant is interesting, but for the most part, finding something new that's a novel intervention is much more likely to be published than something that's not significant. So things go in the file drawer. And why is this a problem? Well, when we put things in the file drawer, we lose some of that effect size. And I'm going to just make up something random. I don't really know if this is a problem or not with this, but let's say the literature on hypnosis for smoking cessation. And let's say I did a study on hypnosis for smoking cessation. I found a significant result. I'm going to try to write that up. I'm going to try to publish it. Let's say 10 other people tried that same thing and it wasn't significant. Theirs all goes in the file drawer. My significant result gets written up, and that's what is known to new researchers or new clinicians. And they're like, wow, hypnosis works well for smoking cessation. But they don't know about those 10 other studies, and that's a problem. So non-significant results not being published biases our results, and so we don't know what really is the true effect because there's a bunch of them that are in a file drawer. So one of the things that's kind of a neat area is looking at the FDA, and the FDA has to keep all of the drug studies have to be kept. All the results of the drug studies have to be kept. So we have a unique opportunity to look at how the effects of non-significant results affect what's actually published. So this is, here's a better, so there's 38 studies. Let me just go up to this one. So there were 38 studies that were found that were non-significant, or 36. 22 of these 36 weren't published, so they went into the file drawer. So looking at a new SSRI, didn't find a significant result. The results go in the file drawer. The FDA actually has these results though, so we can look at those effects. 14 of these studies were published, but maybe manipulated the results a little bit. So this medication didn't work for what we were thinking it worked for depression, but it helped people sleep better, or it helped with this. So they'll publish it with these other results, but not the depression results. Or, so the data is massaged to show what is significant. So when we actually look at the results of the SSRIs, and what we found, and some of these may not even be on the market anymore, but when they took all of the results, the ones that were in the file drawer and the ones that were published, some of the medications had a much less efficacy. So something like Cerazone was found to be 69% less effective if we counted the file drawer studies. So all of the ones that were published showed it worked, but then when we put in the other X number that didn't show a significant result, it's now 69% less effective. And we can see many of these SSRIs were much less effective than thought because a lot of the results weren't published. And this is something that, with pharmaceuticals, we can actually see the results. How is this in the field of psychology where we don't see all the things that are in the file drawer? We only see the things that are significant. So that's a big problem that probably exists in our field in psychology, that we're having the same file drawer problem. Our results are not as significant as we think they are, and I think that's part of this replication problem that we're seeing, where a lot of these classic studies aren't being replicated, and it might be because they were other studies were in the file drawer and the one that was significant was published. So this is something that's really important, and many people have talked about ways to solve this problem. One way is when you design a study, you send the design to the journal, say, I'm going to do this study, will you publish the results, significant or not? And so they're looking at the innovation of the study itself and not as the results. And the choice of publishing it is done before the results are even known. And that's kind of a neat way to do things. Other journals have tried to push for publishing non-significant results. That's got some different success rates. So there actually is a journal of non-significant results, so that all they do is publish non-significant results. But I don't know who's reading that journal. I don't know if it's even published anymore. So the Journal of Non-Significant Results is probably not that interesting. So again, we run into a problem. But if you're doing a meta-analysis, you can comb through that journal and find the non-significant results and get a better estimate of effect size. So these strategies are helpful, and at least we're acknowledging that there's a potential problem with this, that with null hypothesis testing. Again, I think publishing effect sizes could be a big solution for this. Instead of a null hypothesis test, significant or not, how much of an effect. And if we have very little effect, it's probably not that worthwhile of something to do. But I think we have to see this effect over and over again over time to determine how big of an effect we have.